Assalamu alaikum. Okay, we will continue by the course of thermodynamic. بالمحاضرات السابقة تحدثنا عن zero law of thermodynamic, first law of thermodynamic, second law of thermodynamic, and now we will discuss the third law of thermodynamic. إذا القانون الثالث بالديناميكا الحرارية. Third law of thermodynamics talks about the entropy. So the entropy of a perfect crystal at 0 Kelvin is zero. If we talk in material science, we have know about the crystal, the perfect crystal, and the impurities in the crystal. So this is a perfect crystal. This means that um, there is no impurities in the crystal. Means everything in its place. No distortion, no change the molecule between two atoms. So perfect crystal is everything in its place and no molecular motion. There is no motion for molecular in the perfect crystal. So the entropy of perfect crystal at 0 Kelvin is zero, and it is impossible to reach a temperature of absolute zero. This means 0 Kelvin. It is impossible to have a Carnot efficiency equal to 100%. This would imply that T at cold reservoir equals zero. So T at equals 0 Kelvin, this means the entropy is zero. And when the temperature greater than 0 Kelvin, this means the entropy is greater than zero. Okay, this is the molecule and the diable molecule. You can see this the arrangements, and there is in B there's some change in direction for the molecules. Then, if we look to the entropy curve between us and the entropy and the temperature, so in solid it's linear, and then we have fusion, and after goes to gas as vaporization. Okay, so as this absolute entropy can be calculated for any substance for macrostate in sample, this means the entropy is K equal ln omega, and this is K is the Boltzmann constant, and omega is the number of times of probability. We will talk about this soon. So وتساوي إذا كان عدد المرات واحد. So Boltzmann في لأن الواحد تساوي زيرو، إذا which equal zero, the entropy. So for substance in internal equilibrium undergoing an isothermal process, the entropy change goes to zero as T in Kelvin goes to zero. So we can take the limit of the change of the entropy as temperature goes to zero, which equal zero. So the law is valid for pure substance and mixture. If we have a pure or mixture, this law can be applied for entropy. Close to 0 Kelvin, the molecule motion have to be treated using quantum mechanics. إذا إذا عندما إذا اقتربت من 0 كلفن الموليكول، فحركة الموليكول موشن راح نستخدم بهاي الحالة الكوانتم mechanics. So still it is found that quantum ideal gas obey the third law. إذا the quantum mechanics for ideal gas راح تخضع للقانون الثالث بالديناميكا الحرارية. إذا the entropy كمان مرة إنه K B بتساوي لن الأوميجا S. This is as the entropy omega, the number of ways of arranging the component of the system having equivalent energy. And K is the Boltzmann constants, and this Boltzmann constants equal R over Na, where R is universal gas constants and Na is Avogadro number. And we know that the Boltzmann constants, which equal 1.38 في 10 القوة ناقص 23 جول لكل كلفن. So a system with relatively few equivalent ways to arrange its components, smaller omega, has relatively less disorder and low entropy. Even less disorder, this means low entropy. And a system with many equivalent ways to arrange its components, larger omega, has relatively more disorder. And if we have more disorder, it means it's high entropy. And we know, we define the entropy about the order and this about the disorder in the previous lectures. From statistical view من مفهوم الميكانيكا الإحصائية للإنتروبي، entropy and multiplicity S تساوي K في لن الأوميجا. This is called Boltzmann entropy equation. Omega is multiplicity associated with configuration whose entropy we wish to calculate it. So for example, if we have two particles and at volume 1 with state 1 and its change to state 2 at constant temperature with two V1. So نشوف الفوليوم ضعف V1 وانتقل من البارتيكل أو المولكيول من ستيت 1 إلى ستيت 2. فأس1 أس1 تساوي كي بي في لن الأوميجا 1. أما أس2 الأنتروبي لأس2 تساوي كي بي في لن الأوميجا 2. The change of the entropy which equal S2 minus S1 وتساوي KB في لن الأوميجا 2 minus KB في لن الأوميجا 1. لو احنا بنعرف من خصائص اللوغاريتميك انه الناقص ممكن نقسمه، فبالتالي K في B عامل مشترك ناخدها في لن الأوميجا 2 على الأوميجا 1. اوكي، فلن الأوميجا 2 فإحنا بنشوفها اللي هي عبارة عن إيش؟ 2. أوكي، 2 على 1. سو كي بي في لن 2 الأوميجا 1 على الأوميجا 1 وتساوي كي بي في لن 2. And just know about the ln 2 and we multiply by Boltzmann constants, and this is the change of the entropy. Okay, so بالاحتماليات إذا بدنا ناخذ التعريف الانتروبي بالاحتماليات، فأوميجا 2 على أوميجا 1 تساوي V2 على V1 for 1 mole of gas. The change of the entropy from V1 goes to V2 equal R fill in ال V2 على V1. For N mole of gas, the change of entropy for V1 goes to V2 equal N في R fill in ال V2 على V1. Okay, measuring the entropy. كيف بدنا نعمل نقيس الانتروبي؟ So even if we cannot calculate the entropy, we can still measure it. For V, volume constant, and N constants, so the entropy, the change of the entropy ds equal du by t, and du equal dq over t. Here is the work is equal 0. And dq equal cv لا as a function of t في dt على t. So ds also dq by t holds for all reversible or quasi-static process, even if the volume is changed in the process. إذن هاي نثبتها بالreversible or process حتى لو إنه الحجم راح يتغير أثناء العملية. So this is the thermodynamic definition of entropy, which clauses introduced in 1854 long before Boltzmann gave his statistical definition of the entropy, which equal K في الأوميجا. Okay, إذا S لتي ناقص the entropy as a function of zero, which equal the integral from 0 ل t في c في t prime في dt prime over t prime. Okay. Example, by heating a cup of water 200 gram CV, the specific heat at constant volume equal 840 joule لكل Kelvin from 20 Celsius to 100 Celsius. We increase its entropy by delta S, which equal the integration from 0 equal 293 Kelvin ل 100 سلسيوس اللي هي 373 كلفن في سي في اللي هي 840 جول لكل كلفن في دي تي برايم على تي برايم، وهاي تساوي 202 جول لكل كلفن. Okay. So at the same time, the multiplicity of the system is increased by exponential 1.5 في 10 القوة 25. But when the C goes to 0 as T goes to 0, ST minus S0 تساوي 0 ل T ب C في T prime dt على T prime, so C ل T goes to 0 as temperature goes to 0. For example, let's fix the pressure. dq بتساوي the specific heat at constant pressure as a function T dt تساوي the integral from 0 ل T ل dq على T prime، وتساوي الانتجرال from 0 ل T the specific heat at constant pressure T prime dt prime على T prime, and this is finite, so Cp as a function of 0 equals 0. Similar, considering the volume is constant, so Cv to 0 تساوي 0. Thus, the specific heat must be function of a temperature. We know that at high T, Cv approached to a universal temperature independent limit that depend on n and number of degree of freedom. This high temperature behavior cannot presses down to t equals zero. In this case, quantum effect will come into play. إذا في هاي الحالة راح نستخدم الكوانتم ميكانكس. Example for a mole of aluminium CV تساوي AT زائد B في T cube at T less than 50 Kelvin, and this a constant equal 1.35 في 10 قوة ناقص 3 جول كلفن سكوير, and the constant B equal 2.48 في 10 قوة ناقص 5 جول على K to power 4. So that the linear term due to mobile electrons, the cubic term due to the crystal lattice vibration. Find the entropy of the function of time and evaluate the entropy at T equal 1 Kelvin and 10 Kelvin. So the entropy as a function of T equal integral from 0 to T the CV T prime dt prime over T prime, and this is equal the integral from 0 to T, and we substitute the CV. So A في T prime زائد B في T prime cube T prime over T prime, and if we integrate this equation which equal A في T زائد B على 3 زائد B على 3 T cube. Okay, احنا هون just we separated A T prime over T prime integral زائد integral B T cube على T prime dt prime. And for 1 Kelvin, so the entropy at 1 Kelvin just substitute in the equation, and this is gives 1.36 في 10 قوة ناقص 3 جول لكل Kelvin. So at low T, nearly all the entropy comes from the mobile electrons. For 10 Kelvin, as the 10 Kelvin, which equal 2.18 في 10 قوة ناقص 2 جول Kelvin, and this most of the entropy comes from lattice vibration. تتذكروا احنا حكينا انه بالماتيريال ساينس if we heat the crystal in this case نتيجة درجة الحرارة فإما إنها تتحرك أو إنه الأتومز بصير لها vibration, مثل كأنه مثل السبرينج كونستانتس, إنه ماس 1 وماس 2 وبصير لنا إيش vibration. هو نفس الإشي للأتومز أو للموليكولز, إنه إذا كان at low 1 Kelvin راح يكون just from إيش mobile electrons الانتروبي, لكن كل ما زدنا درجة الحرارة, إذا ارتفعنا بدرجة الحرارة, الانتروبي تنشأ عن نتيجة اهتزاز الموليكولز اللاتس فايبريشن. هاي راح تشوفوا شو يعني lattice solid states, what you mean by lattice vibration. This is the distance between two atoms in molecules. Okay. Then, if we go to S1 for KB over KB, وتساوي نرجع لأن الأوميجا قد إيه في عندنا arrangements, فتقريبا 10 القوة 20, and here is 1.6 في 10 القوة 21. So much less the number of particles, most degree of freedom are still freezing out. فمن المهم أحيانا نتعرف على خصائص الماتيريال at low temperature. المقصود ب low temperature means by from 1 Kelvin to 270 before reach the room temperature. It's important to know what's happened for the material when for optical, electrical properties, and so on. Another example, imagine that one macro portion of combined system of two Einstein solids has an entropy 1 joule per Kelvin, while another, where the energy is more evenly divided, has an entropy of 1.001 joule per Kelvin. How many times more likely are you to find the system in the second macro partial compared to the first? So we take the properties of 2 to properties of B1 وهي تساوي أوميجا 2 على أوميجا 1 and we أوميجا 2 على أوميجا 1 تساوي الإكسبوننشال. طبعا هاي جاي إذا أخذنا الإكسبوننشال للطرفين. إحنا حكينا لأن الأوميجا exponential لأن الأوميجا is أوميجا، فبالتالي جاي من الإكسبوننشال نأخذ الإكسبوننشال both sides وتساوي أوميجا 2 على أوميجا 1 exponential to S2 على كي بي ومقسومة على الإكسبوننشال S1 to power S1 على كي بي and just substitute this value and which equal exponential 7.2 في 10 القوة 19. طبعا this is a ratio, there is no units. إذا هاي هي الاحتمالية and the E is العدد النيبيري which equal 2.7. Okay, this is the end of this lecture and thank you for your attention.